Hello, this is Team FuzzML, and our project is generating seed input for JavaScript interpreter fuzzing. Fuzzing is an automated black box software testing method where malformed inputs are given to a program to find bugs or get crashes. Fuzzers have historically achieved low coverage on JavaScript interpreters. This is because the JavaScript engine is multi-stage pipeline where program has to pass both semantic correctness as well as has to be semantically well formed. Prior work before 2018 has been using probabilistic grammar to generate programs, but it has achieved low well-formedness. More recent work has used machine learning and deep learning, and the current state of the art is Montage, which uses LSTM model and trains it on a sequence of abstract syntax tree subtrees. About 80% of the generated programs were well-formed.
Our task then is to improve the well-formedness of generated programs as compared to prior work. And in particular, we're looking to improve two things: syntactic and semantic well-formedness. Syntactic well-formedness means that the generated programs can be successfully parsed, while semantic well-formedness means that the programs can be fully executed without errors. To do this, we train a model using a corpus of 150,000 JavaScript files that have been sourced from GitHub by prior work. So our approach was inspired by looking at the kind of dataset encoding that prior work was doing. So if we take a particular program that's in the corpus, like this function fx, return x plus 5, prior work did many different levels of abstractions of encodings, and these different levels of abstraction allowed the model to better generalize the source corpus. At the base level, you have character level encodings, where individual characters in the corpus are tokens in the vocabulary. And then at the highest level, you have Montage, which parsed the source programs as ASTs. And then as the individual tokens in the model were subtrees of these ASTs, and it used that to get 80% well-formedness. We thought that this might be a little too abstract in the sense that you might be losing some information. So we tried an approach that was a little bit more concrete in the sense that we take rather than subtrees, we have individual ASC nodes, or the types of individual ASC nodes as the tokens in our corpus. So the way that our dataset encoding works is that if we have a program like var a equals 1 plus 2 in our corpus, we parse that into an AST that's on the left, and then we serialize that AST by doing a traversal and then writing down the types of all the nodes. So sequences of these AST nodes make up our training data.
Our FuzzML architecture is made up of an embedding layer, two LSTM layers, and a final linear layer. On conducting hyperparameter search, we found that lowering the learning rate improved the model. Next, we measure the well-formedness of generated programs for each model by first generating 5,000 outputs and then extracting programs from these outputs. Then we run each set of seeds on the Node.js interpreter and measure syntactic well-formedness and semantic well-formedness. Finally, we measure the diversity of generated programs and we evaluate those on the character level LSTM baseline, the DeepSmith model, the Montage model, and the FuzzML model.
As for results, our model improves upon the existing state-of-the-art Montage model in terms of the percentage of semantically well-formed seeds. The generated programs are also as diverse as that generated by the DeepSmith model, which means that our FuzzML approach generates both well-formed and a non-trivial reasonable set of programs. As for the conclusions and future work, we see that encoding programs as sequences of AST nodes is a promising approach for using LSTMs to model programming languages. We also see that there are diminishing returns in increased abstraction of the program encoding. By this, we mean that our approach that was less abstract using AST nodes could generate more well-formed seeds than the Montage approach that used a more abstract approach with AST subtrees. As for future work, we want to look at joint optimization with a loss function that encodes program diversity, which will be useful for fuzzing.